So in this video we're going to look at the Nobel Prize in Physics for the year 1905, awarded to Philipp Lenard for his work on cathode rays. This is from the official Nobel Prize site, and it says, experiment conducted in the late 19th century on cathode rays, radiation emitted when a voltage is applied between two metal plates in a glass tube filled with low pressure gas, led to the discovery of electrons and X-rays. In crucial experiments performed by Philipp Lenard beginning 1893, the glass tube was fitted with a thin aluminium window, making it possible to study the radiation outside the tube and thereby prove that it was not electromagnetic in nature. I said this is from the official Nobel Prize site. So is this. This is his Nobel Prize diploma, beautifully decorated as always. And here some biological information summarized by me, also from the official Nobel Prize site. In 1888, Lenard worked with cathode rays. Hertz said that these were analogous to UV light, but unlike UV light, cathode rays did not pass through a quartz window in the wall of a discharge tube. In 1892, Hertz discovered that uranium glass covered with aluminium foil and put inside the discharge tube became luminous beneath the aluminium foil when the cathode rays struck it. Hertz suggested that it would be possible to separate, by means of a thin plate of aluminium, two spaces, one in which the cathode rays were produced in the ordinary way, and the other in which one could observe them in a pure state. Lenard did this, and he discovered the so-called Lenard window. In 1894, Lenard discovered that the plate of quartz that could be replaced by a thin plate of aluminium foil thick enough to maintain the vacuum inside the tube, but thin enough to allow the cathode rays to pass out. It became possible to study the cathode rays outside the discharge tube. Lenard concluded that the cathode rays were propagated through the air for decimeters and in a vacuum even for meters. Lenard extended Hertz's work on the photoelectric effect, working in a vacuum, showing that when the UV light falls on a metal, it takes from it electrons, which are then propagated in the vacuum, and their speed can change in the electric field, and their path can also be curved by a magnetic field. The numbers of electrons projected is proportional to the energy carried by the incident light, whilst their speed is quite independent of this number and varies only with the wavelength. This conflicted with theory until 1905, when Albert Einstein explained this photoelectric effect. He got the Nobel Prize for that too, not for relativity, but for this explanation, in 1921, I believe. Lenard invented a photoelectric cell, the free electrode lamp. In 1902, Lenard showed that an electron must have a certain minimum energy before it could produce ionization when it passed through a gas. In 1903, he published his conception of the atom as an assemblage of what he called dynamites. The work contributed much to Lorentz theory of electrons. Here you see a Crookes tube, and it is changed a little bit by Lenard. Here you have that aluminium sheet through which the cathode rays can pass. That was a novelty, Novelty. Okay. Then from the award ceremony speech by Professor A. Lindstad, also from the Nobel Prize site and summarized by me. The discovery of the cathode rays forms the first link in a chain of brilliant discoveries with which the names of Röntgen, Becquerel and Curie are connected. The discovery itself was made by Hittorf as long ago as 1896. Cathode rays are a phenomenon which occurs when electricity is discharged in a rarefied gas. If an electron current is led through a glass tube containing rarefied gas, certain radiation phenomena appear both in the gas and around the metal wires or poles through which the current is carried. These phenomena change in form and nature if the gas contained in the tube is rarefied even further. At a given low pressure of gas, rays are emitted from the negative pole, called the cathode, which are invisible to the naked eye but can be observed through certain peculiar effects. This is due to the fact that when these rays hit walls of the glass tube or other obstacles in their path, they cause them to glow or fluoresce and are able to bring objects against with which they are directed to a glowing heat. Like the rays of ordinary light, they propagate in straight lines, but they differ in that they can be deflected from their straight path by means of a magnet. That's not possible by light. The general characteristics of these cathode rays has been known for a long time, although not sufficiently to clarify their true nature. 20 years ago, two basically different concepts were prevalent. According to one concept, cathode rays consistent, as do normal rays of light, of undulating motion in the ether. According to the other concept, cathode rays were supposed to consist of particles which were ejected from the cathode and were charged with negative electricity. The decision for one of these theories rested on the results of experimental research. These were greatly impeded by the fact that one seemed to be restricted to phenomena within the glass tube itself, since the cathode rays ended at the wall of a tube. The question of whether they could exist at all outside the tube remained unanswered. These were the circumstances when Lenard began his work on cathode rays in 1893. He started from a fact which has been observed by Heinrich Hertz, that these rays were able to pass through thin metal plates which had been introduced into the discharge tube. At Hertz's suggestion, he utilized this fact in an attempt to lead the rays out of the tube. He used for this a tube which had not wholly been made of glass, but terminated at one place in a very thin aluminium plate. We saw this just then. As the cathode rays reached Lenard's aluminium window, it was found that they passed through it and continued their course in the air outside the tube. This constituted a discovery which was to have the most far-reaching consequences, above all for the study of the radiation phenomena themselves. It became possible to study cathode rays under much simpler and more convenient experimental conditions than before, and also to separate observations on conditions needed for the production of rays in the tube from questions concerning their propagation and other characteristics. They could be done outside the tube. Here you see the model that Lenard developed for how an atom is constituted. You see here the positive and negative charges are together inside a sort of nucleus. And here you see his apparatus. Here you have the cathode, here you have the anode. Light falls on the cathode and liberates electrons. That's the photoelectric effect. Okay, we continue. Lenard found first of all that the rays coming through the aluminium window possessed the same characteristics as those previously noted in the rays inside the tube. That is, that they cause fluorescence, can be deflected by a magnet, and so on. He further proved that cathode rays have certain chemical effects, such as causing impressions on photographic plates, ionizing air, making gas conducting through so-called ionization, ozonizing air. Sorry, I said it wrong. It was also discovered that these rays pass unimpeded through empty space, but that in gases they are subject to diffusion, which increases the density of the gas, and moreover, that bodies in general differ in permeability as to their absorber powers. There's direct relation to their density. Cathode rays proved to be carriers of negative electricity even in empty space, and they could be deflected from their path by both magnetic and electrical fields. Finally, Lenard showed that these are various types of cathode rays, differentiated among other things by the fact that they are deflected by magnets to a greater or lesser extent. He also found that the formation of one or other type of ray is determined by the degree of gas rarefication in the discharge tube. When Lenard began his work on cathode rays, he approached this concept of their nature from the viewpoint whereby the rays are explained as being vibrations in the air. Through the results of his work, which were just briefly described, in particular through the discovery that the cathode rays are influenced by electric fields, this view became untenable. He now came closer to the view that the rays are composed of particles which are ejected by the cathode and are bearers of negative electricity. This theory has to be modified in several technical details in order to reconcile it with the phenomena which have been brought to light through the work of Lenard and others. It was shown, for example, that these particles, which according to Cruz are ejected from the cathode, the so-called electrons, must have a considerably smaller mass than chemical atoms, and that the velocity of these electrons come about to 1/3 of the speed of light, but there are also cathode rays which are considerably slower. The various types of cathode rays are in fact explained by the different speeds with which they are ejected from the cathode. In more recent work, Lenard has been able to produce cathode rays with relatively slow speed. This research by Lenard has been followed by a series of valuable studies by other scientists as well. Development of the theoretical basis for the study of electron has gone hand in hand with the experimental work. The study of electrons, their characteristics and their behavior in relation to matter has been given a sounder basis through these researches on cathode rays and has been gradually developed into one of the foremost theories of modern physics by himself and other workers. This theory is in fact not only important for the explanation of the cathode rays and other closely related phenomena. The electron theory with its concept on the constitution of matter has become the most fundamental importance for the science of electricity and of light and for both the physicist and the chemist. It is clear that Lenard's work on cathode rays has not only enriched our knowledge of these phenomena, but has also served in many respects as a basis for the development of the electron theory. Lenard's discovery that cathode rays can exist outside the discharge tube, in particular, has opened up a new field of research in physics. It gave an impetus to the search for other thus far unknown sources of similar rays. Well, again, this is a summary of the award-winning speech. It's not a complete speech. If you want to read the complete speech, you can follow these links. This is also in the description under the video. Yeah. Okay. Here you see another of part of Lenard's works, which is less gloriful. We come back to that in the next video. He was involved with the development of a theory called Arische Physik, or German physics, which was an attempt to marry physics with natural socialism. An unfortunate event, but it did happen. We'll come back to this in the next film on this subject, which will be posted next week and will also contain a summary of the Nobel Prize lecture given by Lenard. Again, thank you for watching and maybe till the next time.